Okay, so welcome again to Energy System Modeling course lecture number 3. And today we're going to be talking about consumption modeling. So last time I showed you, the last couple of times I showed you the really small energy system model that we went through. Let's see if I can still find it from my examples. We watched the Monte Carlo simulation, for example, based on this. So in here, I have this curve, which is the consumption. And as you can see there, I'm just using gamma distribution. And I'm summing up 2 gamma distributions. So where does that come from? How much consumption would you actually require in that kind of a system? That's just made up. So now you're going to see some ideas on how to achieve such a load profile. And I'm trying to keep this course on a level that it's not going to go too deep into mathematics, but we're not on the other side trying to stay really on an elementary level either. So throughout this course, I'm trying to kind of anchor these 3 levels: household level, city level, and country level examinations. And these are also present in here. So we're going to see what affects to these profiles. Then we're going to see a lot of modeling approaches. A lot of them will just be kind of introduction to those ones in a way that I'm going to mention the term, so you're going to have something to look up later on. We're not going to go into too much details into there. And then examples on consumption modeling. So let's start with the household level consumption behavior. And the behavior is a word that you have to kind of take into consideration in all of these models. So behavior of human beings makes the load profiles in a way that they are. So key characteristics related to this household level consumption is the, well, in all consumption behavior, usually temporal variations. There are some facilities that run pretty much on flat consumption, flat meaning that it's constant. But for example, household constant usually never remains constant for longer than like 15 minutes or an hour. It always changes. So there are daily cycles. Peak demand typically occurs in the morning and evening when the residents are active. And how to model that? There are these behavior models to account for these factors. But usually the behavior models have also some information from the past. So you have this time series. This is actually from my household again, since I have good access to that data, Eleni ja Aina. And you can see that's the time in days. So maybe this would be the morning spike in here, and that would be the evening spike in there. But I'm not sure if that is actually from any kind of household activity. Rather, it could be these heating spikes. And if you have this consumption data as such, and you don't have the kind of information from the behavior of those occupants and the weather, you don't do much with this. You can see, of course, how much it spikes in here and so forth, but you have to couple this with the environment data always. Seasonal differences, higher energy consumption during winter for heating in colder climates like Finland. And that is especially true, and I can see it in my electric bill. and weekday versus weekend. So if it's household versus if it's industry, there's going to be a distinct difference. More consumption during weekdays due to home office activities or on weekends due to increased presence at home. So you have to be aware of the consumption plays. Yeah.
One day, because I have confused time. How do you have label time?
202. Yeah, this is how many. So this would be pretty much autumn. So 365 days in a year. So this would be 202nd day of the year and so forth from my household. So there's a really small, narrow point from my household consumption. There's 2 days worth of consumption in there. So 202, so it goes from there till there. So that's 1 day, and there's the other day. Yeah, 2 days. And as you can see, there are no observable peaks in there, in a sense, in the morning and in the evening. Maybe this one and this one, but as I said, it might be associated more to the heating system getting or being activated due to the external temperature. So from here, this was one consumer, and in here you can see energy consumption of group of 1,000 residential customers with average usage patterns. So you're averaging out, you're aggregating data. You're well, we're going to talk about aggregation later on, but the usage breakdown, heating is usually dominant in these Nordic climates. Electric or district heating systems. And remember, energy consumption is not just electricity consumption. And in a sense, this heating consumption might be harder for the household consumer if you have district heating systems. It might be harder to kind of obtain the time series out of that one. But either way, it has a similar profile as in with the electrical heating systems. So some kind of a peak. Of course, it's highly dependent on the outside temperature. But if you're talking about the heating systems, it always, or usually it incorporates the hot water as well. The consumption of hot water during the morning, during the nighttime, or the evening, it's higher. So there are these distinct spikes in there. And you can see if you aggregate, for example, washing appliances during the daytime, it's much higher than during the nighttime. And you can kind of dice these up into smaller and smaller pieces up to the level of one electric appliance. But usually we're interested in this aggregated data. So factors influencing behavior, socioeconomic factors. So income level, family size, and lifestyle. Are you a stay-at-home person, or are you active on going outside? And family size definitely affects to the energy consumption. Actually, I was looking about the yearly consumption levels when my children were born. Whenever there was one of my childs were born, I could see a tiny spike upwards in the electricity production during that year. And of course, the water consumption and so forth. So family size affects technological adaptation, smart home devices, energy efficient appliances, and nowadays, especially when you can make these contracts with the electricity company, that you have this flexibility in your demand. So if there's a lot of electricity demand in the network, you are flexible, so you can tone down your consumption. Behavioral patterns, awareness of energy saving practices, and actually this when you have on your phone the price of electricity, if you are buying this pörssisähkö market priced electricity, it's a really good thing to have some kind of an app or something to show you the electricity price, because whenever there's a high price, it means that there's a high demand and there's much load for the network. And relevant data. We have smart meters nowadays providing data for tracking and analyzing our behavior. So that's something that's, in my opinion, a really good thing for the customers to see their own behavioral patterns. So city level heat consumption, key characteristics, common in Finnish cities. So a lot of the Finnish cities, there's a high high amount of district heating that in Finland, in the cities that are using it. So it's really common in here. It's not the same in Southern Europe, of course, since there is not so much this cold weather conditions or as cold weather conditions during the winter time. But in Finnish cities, it's really common. So significant consumption during winter due to heating demand, and this makes the kind of district heating network operator, it puts them in a kind of a pickle, because during summertime you have barely non-existent consumption. It's only like hot water that you have to produce in here, or for hot water consumption. But as you can see from here, the spikes, the individual spikes in here, I guess this is some daily or weekly average or something like that. So the spikes can be much higher. So in here it's 50 megawatts, but you have to have 10 times almost more capacity than the minimum amount. But we're not talking about the production yet. We're talking about the consumption. So peaks during early mornings and late evenings, and that's mostly due to activity and hot water consumption. So two things affect both of these, city level and household level, especially the outside temperature and also the consumption behavior. So variable demand during transitional seasons during here, and that's something that's usually rather hard to model. And in here you can see, this is from Juhani Kotilainen's master's thesis, this picture. I just changed the labels to English. So there's power, district heating power and outside temperature. So this is a rather small network, but either way you can see when the temperature goes up, the power demand drops. So there's a really, of course, because it's heating, and delta T, so the temperature difference between inside temperature and outside temperature, if that decreases, the heat losses decrease. And I guess it was Juho Vähätiitto from Tampere Energy that said, that was a really good analogy, that if you're thinking about heating a sauna during a summer, it's 20 degrees outside and let's say 70 degrees inside. So there's a 50 degree temperature difference. So during the winter time, when there's 30 degrees minus outside, it's pretty much the equivalent of heating kind of the whole city to sauna level temperatures during the summertime. So that's why these peaks really matter. You have to have the capacity to provide it. So building efficiency, older buildings typically consume more energy due to poor insulation. And this is something that we kind of saw in the top-down model last time when I showed it. There was 1% increase in this building energy consumption. So that originates from the assumption that this building efficiency is going upwards. Urban density, more compact cities often have lower per capita heat consumption. If you're talking about district heating networks, the wider the network, the more the losses are going to be. Challenges integrating renewable energy sources like bioenergy and geothermal heat, because, for example, geothermal heat it's not always meeting the demand of trying to achieve, for example, 110 degrees Celsius for the water temperature leaving from the plants. Geothermal heat usually doesn't achieve that. It's somewhere in the 100 Celsius, for example. So you have to kind of prime it. Balancing peak demand with supply side constraints. So those are the problems, and that's what Johan is trying to tackle in his PhD thesis. So he's using this thermohydraulic modeling tool, this fluid heat program. And that's actually kind of an energy system modeling simulator, but we are not using it in this course. It takes some time to get the hang of that. And country level consumption. So key characteristics, seasonability again in Finland, higher demand in winter due to electric heating and lighting needs. And this is actually something that you can see from Fingrid pages. Fingrid offers this consumption data for you, and they have separated these consumption data based on this consumer type. I'm going to show it to you in a minute. Again, lower demand in summer, sectoral contributions. So there's going to be some industrial consumption. So you can see in here, I'm going to show you was it hourly or 15-minute resolution? In here, you can see 1 year resolution. So if we're trying to model the consumption, you have to pay attention to the resolution again. Is it just like making a scenario that our yearly energy consumption is going to go upwards or downwards? Or are you actually trying to model it in 15-minute or hourly intervals? So residential, industrial, commercial, and others as well. How do their behavior affect the consumption? And peak demand often occurs when there's really cold weather, and managed in Finland by these connections with Nordic and Baltic grids. So that's our savior. And actually, there is one master's thesis that is going at the moment that is tackling kind of this problem of having some kind of a deficiency in energy production. So how big of a probability is there that there's going to be not enough electricity production in Finland? Because there has been a lot of these outages, for example, in nuclear power plants. When there's no wind, there's a high or rather low, really low outside temperature. And if nuclear power plant starts to trip and then somebody cuts our cables, then we're going to be in a lot of trouble. But where can you find this country level, so Finnish electricity consumption data? Is let's go to Fingrid. And I'm going to say, is it open data? I'll search it in Finnish. And I'm going to say kulutus, which is the consumption. And in here, let's switch it to English from here. So there's going to be electricity consumption by user group in Finnish distribution networks. And you can go in here, and this doesn't reach back too far, I guess. Is it 1 or 1.5 years? But either way, you can download an Excel file that looks something like this, that you have the labels in here. And from here, you can see what it means. So, for example, this PE01, apartment blocks, and then there's industry and so forth. So I took the labels into here. So you can see, for example, this one is outdoor lighting. And you can see that I have zoomed it into 3,000 and between 3,000 and 400 hours. So that's kind of, I guess, springtime. And you can see the light amount increases. So there's this kind of a discrete decrease in the energy consumption of the outdoor lighting or outside lighting. And then you can see other the other patterns, for example, industry, in my opinion, is really distinct. That you can see there's Monday, Tuesday, Wednesday, Thursday, Friday, and then there's the weekend. And again, the same thing goes on and on. And if you're trying to check or want to check the overall pattern, let's see, there is some dip during the summer, but this is rather constant. It's mostly related to these working hours when they are consuming the most electricity. So that kind of a behavior pattern can be recognized from there. But then when we look at the apartment buildings, for example, you can see this daily peaks. And now if I change the axis from here, there's much stronger correlation between the summer and winter. So this is something that has been aggregated, so summed up together from the consumer places. And I think this is a really nice and accurate data, and it has been divided nicely into rather many sectors in here. So you can, for example, examine the traffic sector, so the effect of electric cars, for instance. And you can see, for example, how much do they compare if we put the other series into the industry. You can see there's a really low amount of consumption compared to the industrial energy consumption. And in here, I think there's a really wide variability in this electricity consumption during the daytime and versus during the nighttime. I would say the data that you can obtain from here, it's in a rather hard format. So we're going to see how to decipher and get it kind of extracted from there, because for some reason they report everything in a way that 1 hour, all of these values are in here for these places, consumption places, and this is the 2nd hour, and that's the 3rd hour, and so forth. So you have to use, for example, this offset function. Yeah, but that's where you can obtain the data from. What other influences policy and pricing? So real-time electricity pricing influence consumption patterns, encouraging off-peak usage. And this, in my opinion, has been a really good thing, because of not too many people are using this pörssisähkö, so market-priced electricity contracts, but enough that it makes a difference. Renewable integration, so that's the so-called root of all evil, in a sense that it makes the perturbation in our electricity system. And this is an interesting figure, in my opinion. This is from Nelli Putkonen's master's thesis. Well, it wasn't produced by her, so it's from another source, but that's where I first saw this. And this is a really good depiction of how much curtailment do you have to do when you have a certain share of electricity produced by wind power. So, for example, if you look in Ireland, when the amount of wind energy increases, the curtailment, so there's excess electricity you have to heat up the ground, for example, that goes up. But Ireland is an island. So, for example, if you're looking at Denmark has much higher amount of this wind power production, and it still doesn't match the curtailment amount. And that's because it's our Norway's neighbor. So whenever there's too much electricity in there, they can just export it there and import it when they don't have wind power. Yeah, so renewable integration. Behavioral aspects, conservation initiatives and subsidies for green technologies, heat pumps, solar panels, and so forth. And adoption of this time of use tariffs. So that's something that's happening nowadays with the electricity business. So something from the modeling approaches. So consumption modeling, it can be physical and data-driven. So we're going to see a combination in those examples. So data-driven models, they have a higher accuracy because they rely on measured data, but then you have to have that measured data, for example, from this FinGrid side. But you don't have, in some cases, too much of it. Physical models are better for this generalization. They are grounded in fundamental principles of physics and engineering, mathematical equations. For example, the heat demand, Q equals UA delta T. So U being the overall heat transfer coefficient, A being the overall surface area, and delta T being the temperature difference. So you can calculate pretty exactly the house heating consumption with that. So that would be a physical model, or then you can just from the time series see what's been going on in that certain house and make this data-driven model. So what you have to incorporate in here, building characteristics, weather conditions, occupancy patterns, and usage schedules. But the accuracy of these physical models is usually limited by the precision and availability of the data. So for example, do you have the precise measurements of a certain building and so forth, or do you have to make some generalizations? And if you start making or aggregating this heat consumption calculations for multiple buildings, how do you do that? Thermal property estimation, if they go wrong, it makes a difference. Behavior assumptions, you have to make assumptions. They can lead to significant deviations in the results. The data-driven models, on the other hand, they use historical consumption data. But the thing is that if you make changes, then the behavioral model doesn't know how to take that into account if that change hasn't been made before. If you have a neural network depicting your household electricity consumption and then you change the fridge, the neural network might not know what that means. But this physical model does. Advanced machine learning techniques, regression analysis, artificial neural networks, support vector machines, this random forests or gradient boosting. I'm not sure how much we are going to be using these ones. In the exercises, we'll be using this kind of a probabilistic model combined with the data-driven model. But I tried these. I tried to make some example out of these, but I just didn't have the time to kind of get it right. But these are, in my opinion, rather easy nowadays to test in Python, for example, because you can just ask ChatGPT, I have this kind of an energy consumption pattern. I would like to test, for example, this support vector machines approach on making this consumption modeling. So in the context of this energy consumption, data-driven models can achieve much higher accuracy because they are directly trained with this measured data. So they capture a lot of nuances that this consumption or this rather physical modeling doesn't. But whenever there's a change, can you take that into account in the data-driven models? That's the key. So the main limitation in these data-driven models lies in their dependency on high quality and comprehensive data sets. So that's the key. You have to have some kind of a so-called funky data. I remember in 2018, that was the first time under my supervision, somebody used neural networks to make this, or in her master's thesis. And The idea was to make it was energy production facility and air emissions. So how do air emissions change when you change the load? And it was a good match within the range. So they were able to train the neural network well within the range of the data. But the data was, for example, I think it was between 100 and 70% of this load, nominal load. But what happens when it drops downwards? Then the model failed drastically. So that's the same thing in here. You have to have data from really kind of funky behaviors to make these more general. So without sufficient data, it's no good. And in this, it might be hard to understand the causalities. So whenever you have neural networks, then you start to ponder, why is my electricity price, for example, last time in the exercises, why is my electricity price negative? You might not find the reason for that so easily. So that's for the physical and data-driven models. Then you have the top-down and bottom-up models. And remember, there's always kind of a combination of these aspects in your models. It doesn't mean that when you have a data-driven model that everything else is excluded. So top-down models, they analyze energy consumption using these macroeconomic indicators. So GDP, gross domestic product, and population data to forecast national energy demand trends. So how much, that was the wrong model. So there's the top-down model. So you have the macroeconomic factors, you have weather, building structure, and you have the legislation related to these building or the structures rather. So you get the building power profile. It might be hard to obtain this high resolution data, but at least you can obtain the overall consumption, for example, during a month, during a year. Bottom-up models, they focused on detailed disaggregated data, individual household appliances. Then you start to sum those up, you get the household level, then you sum those households up, and you get the power profiles. So remember, aspects of top-down and bottom-up models can be utilized. Then the time series analysis. So this is pretty much a data-driven model. And there are these, a lot of times you'll hear in this or see when you read about the literature on these, you can see this ARIMA, so autoregressive integrated moving average, and SARIMA, so seasonal ARIMA. So they are used kind of to predict. So there's the total consumption in here. This is from this ARIMA model and Python for time series forecasting site. So they have this kind of an example, but this isn't exactly ARIMA, since it's not forecasting anything. The forecast is something like this. I tested the ARIMA and SARIMA in Python for my household consumption. And then when I saw the line, I was like, that's it? But so it gives you the overall trend, what's going on, and it gives you a confidence kind of level in which the value is going to be most likely. So it doesn't give you usually the kind of pattern in itself. It gives you the average, and then it gives you a confidence level. But sometimes that's enough. So useful predicting future energy demand based on historical consumption patterns. So, for example, in here you can see the colored lines represent actual values, gray shaded areas represent 95% confidence intervals in the forecasts. So you can see the further the forecast goes, the less confident the model is that it follows this line. So short-term forecasting, ARIMA and similar models are often used to forecast short-term energy consumption, daily or hourly demand. demand response, they help in predicting energy demand fluctuations, and also these long-term predictions. But you always have to take into account the variability in the data. Is this kind of a time series analysis, is it really kind of enough for my needs? Because this is just looking the existing data and nothing else. These machine learning techniques, as we last time saw, these neural networks, for example, they can be used to determine the outcoming events, electricity prices, but then you have to have training data, and you have to have some kind of a scenario what's going to happen. Advanced forecasting techniques, these random forests and gradient boosting, they combine these so-called multiple weak learners, the decision trees, and they can handle both linear and non-linear relationships in data. And I tried, as I said, in Python a lot of these, but I couldn't kind of make up a good example out of these. We'll see if we'll be using these in the exercises. I don't know if we have the time. So this is known for its performance in forecasting tasks due to its ability to handle this kind of a missing data, and for example, this overfitting noisy data sets effectively. Support vector machines, powerful tools for regression. And that's something you might want to, I might actually add a video link in here for you to see what that support vector machine does. But that's again a term that you might want to be familiar with. And again, this deep learning related to neural networks. So convolutional neural networks, long short-term memory, they are increasingly used in this complex models. But they have the same problem as was said before, that usually the causality, it's really hard to determine. So what makes my electricity price go negative? Why doesn't it go below a certain cap? That was, for example, what happened in Siiri Lampela's work. We were having troubles to understand why the electricity price doesn't go below a certain cap. There's the gradient boost method model that's been used. This is from Italy. So this red line is just an average. There were certain electricity areas in there, and this is an example out of one of those. So there's a high variability in it. So it's kind of like a lot of noise in the data. And this gradient boosting method has been used in here. So you can access the article in here. That's just an example how well it predicts that. Then the simulation models. The fluided heat, for example, that I mentioned, that's a similar simulation model, but that's for the entire district heating system. But you can have, for example, these simulation models that are for households. And this is, for example, this IDA ice that was used in one of our master's theses. So they were modeling this effect of this I'm forgetting the word. It was about, is it like passive planning? So it was about the balconies. How much, what kind of a balcony are you going to make? So how far do the edges extend? Is it going to be concrete? Is it going to be glass? Because that affected a lot on the internal temperature. But you can, rather than, well, yeah, it can be used for consumption modeling really well, because it takes into account the weather conditions, and you can make really exact kind of models related to what what kind of a structural elements do you have in there. So from that kind of a model, you could, for example, get the aggregated amount of energy produced in certain zones in a month. It can calculate it in smaller intervals as well. For district heating systems, you can use these. So this fluided heat is one such system, or simulation model rather. So you can analyze load dynamics, energy efficiency measures, renewable energy integration, and so forth. But it can be also used to some extent to consumption modeling. And the simulation programs, so they are essentially these physical models. They can make really accurate predictions on what is happening if you change something, and the causality, it's really easy or much easier in these to determine. So you can optimize the systems with these simulation models. Usually when you have a simulation model, then you have simultaneously an optimizer with it, and that's actually something that comes with this fluided heat, for example. Then something about the behavioral models. So they try to incorporate human behavior patterns into these consumption predictions, modeling the impact of occupancy patterns on residential energy use. So how often people are at home, with what kind of a probability are they at home, and so forth. What kind of a usage of household appliances and what kind of a usage of electric car do they have, and so forth. So emphasize how human habits, preferences, and daily routines affect the energy usage, occupancy patterns, appliance usage, and lifetime choices. And they can be extracted from the historical data, and then you can use that behavioral model further. So they usually do not cover the entire target. So you only have, for example, the household appliance usage, but you don't have the heating. So you have to incorporate that as a physical model in there. So in here, for example, with building energy use, this occupant behavior is just one factor affecting this. So it's one kind of tool in your toolbox. On top of that, indoor environment conditions, operation, maintenance. So these are the human influenced factors. And then there's the climate condition, equipment and systems, and building performance. How much, for example, insulation do you have in there, and so forth? What kind of a HVAC system do you have? So household, as an example, occupancy patterns. So how much how often are people at home? And this called Markov chains model is something that's really often used in here. So in that model, the only thing that's affecting the outcome of the next state is the current state. So are you home or are you not home? And then the model makes some kind of a prediction based on probability. Appliance usage, time of use. So at what point are you going to be using the, so for example, the simulation model that I showed you before related to this NATO off-grid military application, where I had the gamma distribution that was made in a way that time of use would be highest in here and another spike would be in here. And that's just to kind of mimic the load or this behavior from households. Cultural and social norms, different cultures have distinct energy or different distinct energy usage habits, preferences for air conditioning or this room temperature levels, and so forth. Economic sensitivity. So this user behavior can shift based on energy prices, and you can divide the population into different groups that have different preferences. So if energy prices rise, are you willing to cut your consumption, and so forth. So behavioral patterns could be extracted, for example, from these kinds of factors: fridge usage, dishwasher usage, stove usage, and computer usage, from which you can get the total power. And you can see there's a peak in here and a peak in here. And this was a really good kind of a Venn diagram. So interdisciplinary research areas of energy, social, and information science. So energy, social, and information science is on the center. So there's data and information, energy, environment, behavioral, and psychology. And I went through some amount of the behavioral literature related to this energy consumption patterns, and it seems there is a lot of that. There's a lot of, for example, this Markov chains model used to this occupancy behavior and so forth. So this is a really extensive literature. So what you're trying to do is taking into account all of that. These are usually the physical models that you're trying to incorporate in there. Then you have the data information, you have the historical data from the consumption, and then you add in this behavioral psychology models into that. And usually this behavioral models can be implemented in this probabilistic kind of models. So they account for uncertainties in, for example, energy consumption forecasts, estimating the likelihood of occurrences. And if you have historical data and nothing's changed in the system, then you can see that with what kind of a probability am I going to have this and this number of consumption. And in here you can see the real and forecast, but then you can see the confidence levels in here. So at which confidence are you going to be having the value in here, and so forth. So they are really good for these scenarios. So uncertainty representation, that's what they do. What they utilize is probability distributions. So for example, I was using this gamma distribution, or then you can use this normal distribution in your models. They can update predictions as new data becomes available. And this is an important factor. So whenever you have more data, then you can incorporate that into your this kind of a model training. So what more values are available? If something changes in the systems, then we're going to change the training sequence to that new data. And there's some methodology related to this. And again, we'll probably be going through some of these in the exercises, but not all of them. So for example, this Monte Carlo simulations, we somewhat briefly looked last time. So that's a good thing to know how to do. So generates numerous scenarios by randomly sampling inputs to estimate the range of possible outcomes. So that's what we did last time. We had the solar production and the wind production, and they had certain probability functions. So that affects to the outcome. Load forecasting, so they can predict peak and average energy loads, helping utilities plan for demand fluctuations. And that's really, for example, I talked about the master's thesis. So how big of a percentage, or how big of a risk rather, there is that there's going to be a shortage of electricity in Finland. And that's actually something that you could based on the available data, start seeing yourself as well. So you can see the outages, for example, from the nuclear power plants. You can see some scenarios up till 10 years, how our energy consumption palette is going to develop. And then you have the data on wind production variability. So how big of a chance there's going to be an outage. And demand response programs and risk management is also this what these probabilistic models can be used. Scaling and aggregation. So I'm thinking at its most simple form, scaling is multiplying the existing consumption data, and aggregation is kind of summing them up. So if you want to scale the system, for example, from one household to, let's say, this 1,000 households, it's not good to just, multiply that one household consumption with 1,000, because not everybody has the same behavior pattern. So in this scaling, you would want to take into account, for example, the probability modeling. So in their example, scaling a single household's energy consumption by a factor of 100 to estimate community's demand, but it's just not feasible if it's really, for example, the time resolution in the data is accurate. If it's really small or high resolution rather, it's unfeasible to use it in a way that I'm just going to scale it up. You have to have some sort of a probability function in there. Aggregation, combining individual data points to represent total consumption for large systems. So you can sum the time series from different sources. This incorporating variability using statistical distributions, it's also something that you could do in here, and according or rather adding the energy consumption of 100 households to calculate the community's total demand. So there's a slight difference between scaling and between aggregating. You can have, for example, multiple houses and you aggregate the data, so you sum it up. But aggregation, it has its problems. So sometimes you have to apply weights to different components before summing them. So for example, in district heating, assigning higher weights to buildings with larger floor areas. So if your kind of system accounts for more in the total outcome, then you have to weigh it more. Averaging, using mean values instead of sums to normalize the data. Calculate the average energy use per household for benchmarking. Temporal adjustments, this is something that we did. Align and resample data before summation. You have to have all the data points in the data set, and then you have to have the same interval. And that's something, as I've shown you in the exercises, in some cases it's rather hard because this data is in hourly intervals, this is in 10 minutes, this is in 1 minute, this is in 15 minutes. How are you going to manage that? Well, now you have the tool in your toolbox of making these smoothing splines and using those to interpolate. Dealing with non-linearities. For example, power grids exhibit non-linear behaviors that require more complex aggregation techniques and statistical analysis. And in here you can see 1 user, 5 users, 20, and up to 80 users. So what that means is it's kind of smoothing the profile. So this is for kind of your information that these kinds of techniques exist. And now what we're going to be using them on, examples on this consumption modeling. We're going to start with the household consumption modeling. And what we're going to be using is my household electricity consumption data from 2023 and 2024. And what I did, I used this gamma distribution based data-driven simulation for household appliances and behavior-linked consumption. Because I couldn't make any kind of a physical model on that. And I'm not going to share any behavioral models from my household. So what we're going to do is we're going to make this data-driven modeling. The model assumes that energy consumption for each combination of season, weekend, and hour follows this gamma distribution, because that's something I kind of saw in my consumption patterns, that this gamma distribution could be utilized. It wasn't normal distribution. There were some tails, edges towards the sides. Parameters of the gamma distribution, shape and scale, are estimated for each group using historical consumption data. So what I'm trying to do is I'm trying to kind of see, let's see if we can draw it in here in the whiteboard. First of all, in the Python code, what I did is when you have the consumption in here, I divide it into 4 seasons. So there's winter, spring, summer, autumn. Yeah, that's how it goes. And then these certain seasons, I divided it into certain, in a sense, weeks, in a way that every weekday has its own mark. So if there's Monday, there's Tuesday, and so forth. And all of these hours, if it's 0 hours, if it's 1, if it's second, third, and so forth, all of those are examined. And from here, I can see that all Mondays during this time, I'm going to see what kind of a consumption does it have in here, in here, in here. On Mondays, hour 1. All Mondays, I'm going to identify them, and all Mondays at time 1 o'clock in the night, I'm going to identify those and see how much consumption did I have at that time. So I'm going to differentiate between days, weekends, hours, seasons. But I have a problem. My consumption isn't only related to this behavioral. So the model generates simulated energy consumption data for the next year based on historical data. Predictions account for seasonal variation, weekends, hourly, so making a time series based simulation. Then I have physical model for considering household heating. And this is something we're going to be going through in the exercises with a bit more detail. So I'm having a physical model for this heating. So Q equals UA delta T. So what that means is I'm going to be able to determine based on the data set what is this UA value for 1 year, and I'm going to be using that for the next one. So I can kind of subtract the effect of the heating from my energy consumption. So outside temperature read from this Finnish Meteorological Institute site, and this 23 is going to be the training data, and 24 is something we'll be testing it on. Household has electric heating, so the household heating can be subtracted from the total consumption. So if we're going to draw it in here, if I have the consumption pattern in here, there's the variability, there's the power, and there's time, and that's 1 year. I have the outside temperature. I'm going to model how much from this one I can subtract. So there's the temperature variability in here, and everything's that left in between here is modeled based on the consumption. And for this, I'm going to be using the gamma distribution. So that's the total electricity consumption during 1 year. And that's 2024 and 2023. 2023 should be 24 hours longer, but maybe I cut the lines because it seems that, or maybe the resolution is not sufficient to see. And if you see it from here, I'm going to be taking the same, that's probably spring, 2100 to 2300 hours. So you can see there's a lot of variability. There's variability due to the weather, and there's variability due to the consumption behavior. So we're going to try to separate that. And how you're going to do that is I plotted every value for this power against the temperature. And when you have the power against the temperature, you can see that there is some kind of this kind of a bottom line there. And that was really hard to kind of find a way to make that in Excel. So it finds all of the lowest points at a certain interval. But again, with the help of Mr. ChatGPT, I managed to pull that off somewhat well. So this is dependent, or this kind of identifies the lowest values used in here. So I could say that everything else about that is related to this behavioral changes. It's not exactly true because in household, the let's say the electricity power doesn't necessarily, in my heating system, it doesn't necessarily mean that if this hour is in here, that because there's thermal inertia, let's say that. So this might be a bit too low values, but that's why we'll see in the results how well did it kind of perform. But this is some kind of an estimation on how much heating is required. Because in here, you can see that if Q equals UA delta T, you can see delta T in here, delta T in here. Delta T increases. So if I make a fit for it, as I've made in I tried making this mostly in Excel. The probability distribution I had to move to move to Python. But in here, you can see that this is the linear kind of function of these values. So what it does, it gives me the delta x delta t, or rather delta y delta x. So this coefficient should be minus UA. So if I'm going to say UA equals in kilowatts, so this one times minus 1000. My UA is this much. And if I'm going to roughly estimate my area of my household, it's like, let's say, 10 meters, roughly 6 meters per side times 4. So let's calculate the U. 0.19. So that's in watts per meter squared kelvins. Meter should be small. So let's go and see. This means in English that I'm trying to check the U values of typical houses. Outside wall, so that's the ceiling, and the bottom, I didn't take those into account, so it might increase the value a bit. So it's in the neighborhood. I think that was a rough estimate that we did, but it's in the neighborhood. So that gives me confidence. So what happens next is I'm using probabilistic modeling. So it takes into account these seasonal, weekend, hourly variation, and so forth. So this is an example of the data set. So those, I put those red lines in there so you could more easily see the points. So winter Mondays at 9 a.m. This is all the data I have. It's not much, but it's honest work. So you can see the dots in here rather represent the how much power consumption did I have. And now if I make the probability density function for it, if I use gamma distribution, it would look something like this. And that is fitted with this Python code. So I have the code in here. So if I run it, by the way, the input is just the behavioral related energy consumption. So now it gathers all the data and makes the probability density function for it. And as you can see, say, okay, we have a limited amount of data, but we'll work with that. So what it's going to give me is going to give me an estimation, or rather, the training data was 2023. So this training, it looks somewhat good. If I use only these gamma functions to make this training data, it looks somewhat good, and it gives me year 2024. So let's see how well that matches up. So that's my prompt, and there was my code. And that's the measured 2024, measured 2024 values and simulated. And as you can see, it's not that bad. If we look it a bit closer, I mean, in here you can clearly see that since my model includes the temperature from 2024, it can make the seasonal heating consumption rather nicely because it follows this kind of a U-shaped pattern. And the consumption model, it's there. There's variation on a similar magnitude. But now if I draw the load duration curve, you can see that it's rather spot on. So the probability distribution model took into account the everything else than heating. So it's behavioral related consumption. And as you can see from here, it doesn't always match the exact same values. But since it's a probability distribution function, it kind of gives me the range where things are happening, and it randomizes them. If I were to run the model again, I would get a different kind of result. But the load duration curve still is rather well fitted. So now I have trained the model based on 2024. I have combined physical modeling and this probability modeling. And I've obtained a consumption model for my household. The same, and where did I get this idea from? The same can be made for this district heating consumption. So this is the modeling city-scale transient district heat demand by combining physical and data-driven approaches. So most of you might be familiar with Peter Lund, a professor from Aalto University. So what they did in their approach was pretty much the same that I did in here. They went a bit further. So they took into account the inertia in this entire district heating system. So again, we're using a combination of physical and data-driven model. We're not using a similar probability model. Rather, we're making this kind of a time series analysis. And we're going to fix this hot water consumption. So physical model is the one that takes into account the temperature change. And data-driven model is the one that takes into account the behavioral, so this hot water consumption. Forecasting heat demand, decomposing heat demand into components, so the outside temperature based heating and hot water. Simplified physical principles for building level modeling, aggregates data to describe overall district heating system behavior and uses, well, maybe not the statistical techniques, but either way. So the model type is a combination of deterministic elements from physical model. And if we were to use this probability distribution model, in here, I didn't use it, so I just fixed the hot water consumption. But you could use this probability element in here as well. So this is from the article. They have yearly profile of district heating in, I think it was in Vantaa. So in here you can see the outside temperature and the district heating. And you see during the summertime, it's rather flat. So if you zoom in on it, you can see this summer profile, weekly district heating profile, and hourly district heating profile. So you can see there's Monday morning, Monday evening, and so forth. So that stays rather constant. And this is the same approach that I used in the household. So I got the idea from here. They do pretty much the exact same thing. They have a certain amount of data points, and they plot the total heat demand against the ambient temperature. So it makes this kind of a curve. So if you subtract the average hot water consumption, that goes to zero in somewhere here. And this is the result. So this is each point of modeled and measured district heating demand. And when you see the long duration curve, you can easily see that the model is rather accurate. So let's try to do that for a certain city inland of Finland. So you can see the consumption of that certain city of district heating in different years, 2021, 22, 23. So we have average data. That's something that's related to this aggregation. And then there's the outside temperature. Again, we can plot or make the model more accurate when we use many years. And there is the consumption against the temperature. And now what I have done is subtracted from here the hot water usage. So this is basically in here just the hot water usage, because during that summertime you don't need anything but you don't need the building heating, you need just the hot water. So the same thing, I found the smallest values in here, and this is actually much more accurate now that we have aggregated data and we have citywide city level data in here. So after that, I was using two normal distribution functions. And if you sum up normal distributions, you get these kinds of spikes. And then I have this aggregated consumption during summertime. So this is 4,200 and 4,300 and something. So there's 7 days worth, or is that 1, 2, 3, 4, 5, 6, 7? Yeah, so that's the weekend. And you can see it's pretty much the same all the time. So on top of that, I use this kind of a parabolic curve function to kind of account that during the winter time there might be a bit more of this heat consumption, or rather hot water consumption. But basically, this is just regression. So I'm fitting these probable or the normal distribution function to account for what's happening in real life. So that's just kind of time series analysis and regression. Combining two normal distributions, making regression fit to describe hot water consumption behavior. Time series point from summer where no building heating is required. And this is what I got. I have the measurement and I have the model. So I'd say that's a rather good fit. And if you look the consumption and measurement in load duration curves, it looks even, well, somewhat even better. In here, what I have said to the model that between 4,000 and 5,500, I guess, in here, just shut down the outside temperature related heating demand. So that's not needed. So that was kind of an arbitrary, well, not arbitrary. It was kind of a forced action to the model. So during this time, there is no building heating. And you can see it kind of, well, it doesn't fail in here, but there are some spikes that the model doesn't account for. How they went past this and beyond in the article, and what I also tried, and that was actually doable in Excel, is that they accounted for the thermal inertia of the buildings. So if I increase heat capacity of the building structures in here, you can see that the variability shrinks a bit. So if I put Control C, you can see in here the variability increases, now the variability decreases. And that is because of the thermal inertia. You can kind of, if there's a sudden spike in the temperature, you can kind of write it out because you have heat stored in your building already. You don't have to make so much, or you don't consume rather so much heat if there's a sudden spike or a sudden drop. So that kind of shrinks it down. We're not going to go into that level of detail in the calculation exercises, but I think that was an interesting technique in there that was utilized. So it's described in the, let's view it from here. It's described in here in the article. So you can see how the building thermal inertia is taken into account in these equations. And it's basically just numerical modeling. So that's one added layer into this physical model that you can take into account. So it's dynamic in a change that it takes into account what's been going on before and so forth. So these are the ones that I think we are going to go through in the exercises, and for the so the country level electricity consumption. This is the data, I think, if you need from Finland something related to that. This is the best data set I've come across. So FinGrid offers this, and you can see that it's multiple user groups that are separated or disaggregated in here. And this is really, really nice. Okay, that concludes this lecture. So for once, we're a bit ahead on time. So hopefully you got some understanding on what kind of techniques you can utilize for consumption modeling and what kind of applications you can use it for. And tomorrow and on Friday, we're going to, in the exercises, go through these ones at least to some extent.